Okay, so let's go ahead and get started since you do have an exam coming up. First of all, I want to let you know that there is a pre-lab for this next week. It's on polarimetry, which hopefully we'll actually get started talking about that. If you don't see the handout available by later on tonight, make sure you just send me an email. I've got to make sure that make it visible on my fire. Okay, but it's completely not 180, but it's a completely different subject than what we're doing right now, and I wanted to go ahead and get through this. Make sure you know how to do this kind of thing. I can pretty much guarantee you're going to see it again. I know I was really hoping that by now I'd have copies, like a physical copy of the book, so that way I could look at the end of the chapter questions and give you more examples of things to work on. But you can even look back at the end of each chapter. They have more problems. If you want more practice with this kind of thing in order to see, get an idea of the kinds of questions that could be asked. Okay, so when we last left off, we were doing di-substituted cyclohexanes. And we've already talked about cis versus trans. We have trans 1-ethyl 3-methyl cyclohexane. Okay, so there's an ethyl group. And once again, many times when we draw things out like this, we're supposed to assume that everything, unless you say otherwise, those sticks would all be methyls. But whenever I'm doing this, just to help provide clarity for what's an axial versus equatorial position, it's fine with me if you just write down, unless noted otherwise, that these are all hydrogens. Okay, since I won't take off for that I won't take off on the handwritten part of the, on the exam. Okay, so I drew in the ethyl. So for this to be trans 1-ethyl 3-methyl, where should the methyl group be located at here? Okay, so we can say the far left. So if this was 1, this would be 2, 3. Or there's another option. If you went clockwise, it could be 1, 2, 3. Okay, that's why since we're talking about cyclical, something cyclical, then we can go ahead and do either or. Okay, but I'm going to go ahead and go with the far left. And then for it to be trans, does it need to be axial or equatorial right now? It's going to be axial. Okay, whenever I draw when it's ring flipped, then in keeping everything else the same, now the ethyl group is here. And the methyl group is like this. And please note once again that I put the carbon, make it obvious that the carbon is the one of the methyl group that is bound or bonded. It's bound. That's in an interaction with the carbon of the ring. Okay, not the hydrogens. So now the question here is, which one of these is one more stable than the other, or are they equal in stability? And then if there is a difference in stability, which one would be more stable? Okay? And so, first of all, are these equal in stability? No. So then we have either option A on the left and option B on the right, but one's going to be more stable than the other. And which one's going to be more stable? A. Okay? So this time, whoops, that's supposed to be a straight line. So stability favors where the ethyl is in the axial position. And why is that true? Because we actually, remember I told you before, we could say, we had one axial, one equatorial, one axial, and one equatorial. But why is it that these are not the same? What makes them that they are not the same in energy? The size. The two groups are not the same size. And so whenever, it'd be true, if this was trans 1,3-diethyl cyclohexane, then they would be equal. Okay, but since we have a methyl and we have an ethyl, there's a clear size difference. You want the one that's larger to be in the equatorial position. This is really true whenever you look at the the methyl ethyl groups, the T-butyl groups, because those are huge. Or if we stuck another ring out there, then you would definitely want to favor, the equatorial position versus the axial position typically. All right, and so like I said, on your own, you'll want to go through. You could also do the same thing, like what happens if we have a cis something that's cis in positions 1 and 4, something that's trans in 1 and 4, cis and trans in 1 and 3, and cis and trans in 1 and 2 positions for the dice substituted. Or you can even make it multi-substituted. Like what happens if you've got, which I can't think of off the top of my head without making, but what happens, like, is there a difference between something like this? Let me. So on your own, you may want to work this out to see, are all of these created equal? Please note, I cannot use the term cis and trans here because we have three things. We can talk about two things being cis or trans with respect to each other, but we can't for when there's three. All right, and so like, is there, you can imagine drawing lots of different possibilities for 1,2-diethyl-3-methyl-cyclohexane, but what happens if one of them is more stable than the others? Or perhaps multiple ones are equal in stability, but one is the worst, or something like that. And so that's why these are the kind of things that if you're given the choice between two different options, you'll have to be able to categorize them as one being more stable than another, or if they're equal in stability. So on your own, you may want to even play around with something like this. There used to be, like I said, I haven't been able to check in the current edition, but there used to be a really good example of this kind of question in the back of the book. Like in the back of that chapter where it gave like a 1,1,2,3 tetramethyl cyclohexane, and how one of the isomers was much more stable than the others, and so what one would it be? And so then you'd have to kind of sit around and use the logic to try to figure out what one would be the best, or so on and so forth. Okay. So now we're going to be moving on to chapter 4, and in this chapter we're talking about chirality. Okay. Please notice it's not chiral, it's chiral with a K sound. And in particular, we have this big old term called enantiomers, or they may say something is enantiomeric. So what does that mean? Well, in general, we may not have used these terms before, but you already should be, you've been thinking about them on this level already. But we have different levels of structure. We can have what it's composed of, which is just a molecular formula, like C6H6 for what we'll find out later on is benzene ring. You can have the constitution, which is just how that they are connected. So you can have like constitutional stereoisomers. Configuration, which is just a fancy term for saying three-dimensional positions. And then conformation. I don't like the definition that they use here for conformation. I just think of it with respect to the shape. Because when we talk about conformations in biochemistry, that's usually what we're referring to. Okay? And so that's why there are different types of isomers. We've already been talking about those that are stereoisomers versus, in Gen Chem you learn the term like geometric isomers and constitutional isomers, things like that. Okay, and so now we're going to be talking about one type in particular. So here, I'm just going to show you this for a moment. A chiral molecule is not identical to its mirror image. And they always talk about it's where they're non-superimposable. And that's kind of, at least for me, whenever I was sitting there, I didn't really understand what they were talking about. And so what I like to do is, your hands are natural enantiomers. Okay, so unless your parents are first cousins or something like that, you should have hands that are mirror images of each other for the most part, and they're non-superimposable. So for example, if you take your left hand, you put your right hand on top of it, and you match up your middle finger, your thumbs don't match up. So they're mirror images, but they're non-superimposable. So that's why they're said to be enantiomers. They're enantiomeric. Okay. So yeah, one time I had a student who she's one of the these kind of people who actually I tend to do this myself, where I say things without thinking about how it sounds. So in class, she does like this, like, "Oh my goodness," She put hers on top of each other, and I was like, "No." It's like, "What's going on? What's going on?" But yeah, she was like freaking out that something was wrong with her. Okay, but yes. Now, in general, chirality, we have a slide coming up. The way that they put these slides, I don't like it. They put this slide all the way at the very end. But chiral enantiomers, actually, they have the exact same boiling point. They have the exact same melting point. They only differ in one, it seems like a relatively minor thing, but it's actually biologically, biochemically, it's very, very important. Does anyone know what is it that they differ in? Like what? They have the same properties otherwise, like melting point, boiling point, for vaporization, all that kind of stuff is all the same, but there's one thing that they really differ in. And so it's how they rotate light, which you think, why is that important at all? But if you take plain polarized light, and we've got a picture of this showing up in a moment, you take polarized, where the wavelengths are only going in one direction, if you think back to physics, whenever it hits, for example, if it hits your left hand, it would refract it in one direction. If you do your right, it's going to go in the exact opposite direction, okay? And so if one of them rotated the light plus 15 degrees, the other one's going to rotate it negative 15 degrees. And so you think, why is that important in biology? Does anyone know why would that be important at all in biology? It's not like we have to worry about beams of light, going through us and like rotating, even though I did have a calc, I'm trying to remember, 1 or 2, I think it was Calc 2 professor. She's technically a TA. And back then we had to do Mathematica, which I think that they're just trying to get started here, but you guys probably haven't had it yet. We had to do calculus labs. And so we had to meet 5 days a week. We were in there for multiple hours, writing computer code and all this. This one was very, very nice. She's from Russia, but we swore she was a vampire. Because this woman was the whitest person, like she was just as white as this dry erase board. That she had no pigmentation whatsoever, but she's dark-headed. And the way that Mizzou is set up at that time, just like a lot of the northern schools, you can go from building to building many times without going outside, because in wintertime it's cold. And so we always thought that she just lived in the math and physics buildings, because she could go underneath the tunnels to go, so she would never have to go outside. But I swear, this woman, when she would walk in front of the projector, like the light shined through her, where she was like a prism. It would be like this little halo-looking effect, and so we knew she's a vampire. And so, but normally, biologically speaking, that's not why. It's not like she has some type of chirality, some special chirality, or whatever. So, okay, why would that be important in biology or biochemistry? X-ray. Well, so possibly with X-rays, but even on a more simplistic level, really simplistic level, just think about your right hand and your left hand. What can one do versus the other? Don't tell me right, because I write with both hands. I can write with both hands at the same time. But what can one do but the other one not do? Just think on the most, maybe not so much here in Florida, but if you're up north, wear gloves. So, once again, with the exception, now we're talking about not like mittens. Like one time I had a girlfriend who knitted me mittens, which that was a very nice and noble gesture. I appreciate the thought, but like, who gives a grown man mittens? Like, how many people were like, what is the whole purpose? So I put them on, I think that one time in front of her, and then I don't even know whatever happened to him since. So, who wears mittens? But that's that one. So, but with gloves, you can't. And the same thing happens in vivo. What do we have that would be like gloves, for example, in our body, where it would really matter? The organic chemistry book covers a little bit, but they focus on not just biochemistry, but also on other aspects. What in your body would be kind of like a glove, in that sense, in vivo? What's one example? There are lots of examples, but what's one? Pardon? Well, what you could say, but what inside your brain? Like, we're talking on a very simplistic level. Receptors. Bingo, number one thing. I mean, not number one, but enzymes, and you can say lots of different enzymes. They have something that has to bind. It's got to fit in just right. So, for example, like I have asthma and everything. So some of you maybe you have asthma. There are two types of like the generic albuterol. There's albuterol and there's levoalbuterol. Albuterol is a mixture, it would be like a mixture of your right hand and your left hand. Lead albuterol would just be like your left hand. So one of them is much better medicine than the other. It's the one that's all left-handed, because otherwise what happens when you take the albuterol, all the right-handed molecules don't fit in correctly. Okay, so typically the lower dose, these are things that usually, these medications usually are more expensive if they are enantiospecific. That's the technical term for it. Okay, or sometimes they may be able to fit in, but not quite right, to where they could even turn off or turn on the receptor. So there are lots of possibilities there. You can imagine, like, what happens if you're trying to put your hand in a glove that's too big. You know, yes, it can fit in, but it doesn't fit in quite right, so it doesn't work quite as well. On a very simplistic level, that can also happen in vivo. All right, so I diverged from that a little bit, but hopefully to give some reasons why this is really important to learn in organic chemistry. And so we have to think about things that are chiral. Chiral are mirror images that are non-superimposable upon each other. Okay, and that's what they're trying to show here. They always like to use the bromochlorofluoromethane. That's what this one is. Bromochlorofluoromethane, because there's a carbon that's got a hydrogen, chlorine, fluorine, and bromine all on it. Okay. So there's a cheating way to do this, and I know that many of you want to be able to, I don't say cheat, but the easy way. Whenever you want to try to figure out if a carbon is chiral. So for carbons to be chiral, this must be an S. Usually, like 99.99999% of the time, all you have to do is think and look, are there 4 different things attached? I'll say, I don't want to say atoms because I'll give examples when it's not true. So I'll use the non-scientific term of things. Okay. So that's why bromochlorofluoromethane works so well, because we have a carbon that's got a bromine. This is not done in 3 dimensions. Chlorine, fluorine, and a hydrogen. So it's methane, because you haven't learned how to name alkyl halides yet. Hopefully you're picking up on it. It's methane if it would be ch4. However, once you add a bromine, a chlorine, a fluorine on it, it becomes bromochlorofluoromethane. We've got 4 different things hanging off. Now, the technical reason why is at no point in time do we have a line of symmetry. Like, if we divide this up any point in time, the left-hand side and the right-hand side are going to be different. Just like if you look at your fingers, once again, unless something's really odd, some type of mutant, you put that line down the middle, there's no point of line of symmetry. Your pinky and your thumb do not line up. You know, most people's ring finger and middle finger wouldn't line up. I say most people because there are some that have roughly the same size. But you shouldn't have the same size pinky and thumb. That would be weird. So, what about something like this? What if it's just bromochloromethane? Is this going to be chiral or achiral? It's achiral. And the reason why is there is a point of symmetry in it. Because if we draw this, let me see if I can get it. That's one of the reasons why I say you just need to look to see if there's 4 different things attached. I'm going to attempt to draw this in 3 dimensions. We have a carbon with the chlorine and the bromine, and they're in the plane of the board here. Then we have a hydrogen going out away and a hydrogen coming towards us. So now you can imagine, I don't know, but many times if you think about it kind of violently, it kind of helps bring it into perspective, that if you took a guillotine and you chopped that in half where in the board, so the guillotine was going in the direction of the board like that, you would find out that you have a plane of symmetry there. It may not be the most obvious, But the reason why, that's why I put the chlorine and the bromine inside the plane of the board, because you could have half of a chlorine on one side. So I don't know if you think about, if you've seen like organisms that have been frozen and then they take the slice for for histological purposes. So we just took that bromochloromethane, we chopped it in half. You had perfectly one half of the chlorine on one side and one half of the bromine on one side. And then you have one whole hydrogen and another whole hydrogen. So that's why there's a plane of symmetry there. It's just within the plane of the board. If I would have drawn it where the two hydrogens were in the board, then it wouldn't have been as obvious. Oh, hopefully, at least for me, it wouldn't have been as obvious. So just in general, any time that you have 4 different things, and it's got to be 4 different things, because I don't think your book really touches on something called prochirality, which can happen. It's not as specific, but that's whenever there's 3 different things. But you've got to have 4 different things. It's called chirality, okay, for carbon. All right, so this is just, there we go. That's just to show you that, yes, there are 4 different groups attached. It's non-superimposable. Therefore, they're called enantiomers with respect to each other. Okay. So, similar to that, this is just to show you, this is identical to what I just did, but I used a chlorine and a bromine with 2 hydrogens, and they're using chlorine and hydrogen and 2 fluorines. But here they're showing that you can actually have them to be, not only is there plane of symmetry, but they are superimposable. I could not have drawn that easily. But we can see here that they are superimposable upon each other. You draw one of them, you imagine a mirror, you draw the mirror image. You can literally move this one over on top of it, and the chlorine's going to match up the chlorine, the hydrogen, and the 2 fluorines match up. So that's why it's called achiral. This is just a little cartoon to show the thing that I told you about having 4 different things attached, W, X, Y, and Z, and how there's chirality. And so it's called a chiral center. Okay. And I want to explain, first of all, the picture kind of has obfuscated some of the wording there. But they're just showing, once again, this whole idea that we have 4 different things. We can write it multiple different ways, but they're going to be chiral. Now, these are just other examples. As 2-butanol, we have a chiral carbon here because it's got 4 different things hanging off of it. Whereas if we had 2-propanol, it's achiral because we have 2 methyl groups. Now, there is this little caveat down here that I want to point out, and I'm going to try to do a better job than what they did here on this PowerPoint in explaining. It is possible that you can have molecules that have multiple chiral carbons, multiple chiral centers, and it be achiral. And so we're going to do an example of something like that in just a moment. Okay, so the easiest way to do that, I think, is just to start in the beginning. So let's look at, and you haven't learned how to name alcohols, but you could probably figure this out. But it's a compound called 2,3, that's a hyphen, it doesn't come out very well, hyphen, butanediol. I'm going to get a cough drop because I'm spitting all over the iPad. Like some type of man llama. Okay. So, how many carbons do you suppose are in 2,3-butanediol? How many carbons are in there? 4. Okay. So we have carbon. I'm going to do it longhand ways. Carbon, carbon, carbon. All right. So 2,3-butanediol. What do you suppose is hanging off of carbons 2 and 3? In alcohol each. The di just means 2. The ol is the ending. Oops. Mm-hmm. here by a moment get caught up. So, do we have any chiral carbons here? Carbons have 4 different things hanging off. So we start right here, carbon number 1. Are there 4 different things hanging off of that carbon? 4 different things? No, 3 of them are hydrogens. So that one's achiral. Okay, so if we go to the second carbon, do we have 4 different things hanging off of it? Yes, so that one I'm going to put a little asterisk by. That's a chiral center. What about carbon number 3? Yes, because we have, just to review, we have an alcohol, we have a methyl, a hydrogen, and we have all of that. And then the 4th carbon, is it chiral or achiral? It's achiral. So, is this molecule going to be chiral or achiral? That's kind of a trick question because it can be both. The way I have it drawn here, does it have a plane symmetry there? Yeah, you can imagine if we take that guillotine, which I use a guillotine a lot in organic chemistry, and we karate chop it in half, we have that left half is superimposed on that right half. However, at the same time, I could have drawn it this way. Whoops, that's supposed to be the C. And now, the 2 terminal carbons are still achiral, but the 2 middle carbons are still chiral. Okay, and so that's why now there's not that plane of symmetry. So that's what that means by you have to be careful because it is possible, these are still chiral carbons, to have a compound, and I don't know if we'll have enough time today to get around to it. Hopefully we will. We can have a compound that have chiral carbons and still be achiral overall. Okay? And so they give a special name. And we'll talk about it in just a moment. These two, this form down here, it really is chiral overall. And mathematically, we'll even prove that. The one at the top, though, it is achiral. And the reason being is we can see where they line up, and there's now this plane of symmetry within it. They give it a special name. It's called a meso compound. Okay. So I'm going to come back to that, but that's why I wanted to point out on that previous slide, they just said molecules with more than one chirality center may be achiral, but then they leave it. They don't tell you anything like how is that possible. And so I wanted to give an example before we're going to mathematically, we will also prove it. Mm-hmm. Now the next question is, what about a ring? So what about rings? So let's look at some examples here. Okay. So these are just 2 examples. You're going to learn, by the way, I looked, it's chapter 5 that should have the table with the functional groups. I still don't know the exact page number. But hopefully you should start to be memorizing functional groups. We already know a couple. You know alcohol, and then alkyl halides when there's a halogen hanging off. Okay. These are cyclohexane, groups or derivatives thereof. This one on the right, by the way, is called an ether. That's what that functional group is. When you have a carbon, an oxygen, and a carbon, it's called an ether. Okay. Are there any chiral carbons in this first compound right here? Do we have any of the carbons there that have 4 different things hanging off? The answer is no. Okay, because at first your gut maybe say, oh, but look, this one's chiral. But it's not, because when we look at that, if we were to guillotine this one, see right there we have a plane of symmetry. But even if we have to be careful, what we have to do is, if we talk about the 4 different things hanging off of this one, it's easy to be able to say, oh, look, we have a hydrogen, we have a methyl group. Those are 2 different things. But then what are the other 2 things hanging off of it? And so what you do is you start and you go this direction, or the other direction, doesn't matter. You go one direction, we say, oh, look, it's CH2, 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 CH2. When you go the other direction, it's the exact same thing. The order is the same, and so therefore those are the 2 same things. And so this one overall is a chiral. There are no chiral carbons in there. What about the one on the right? Is there a chiral carbon? Yes. Okay, it's this one right here. So I'm going to go ahead and draw the hydrogen. The reason, first of all, is you should clearly be able to tell there is a methyl and a hydrogen. Those are 2 different things. But we also have 2 different things cyclically, to where I'm going to start counterclockwise. And going counterclockwise, it goes CH2, CH2, because there's CH2, 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 so we have 4 CH2s, and then an oxygen. Going clockwise now, it goes oxygen and 4 CH2s, and so technically they are different. Okay, they don't match up. Now, if I would have put the oxygen, another oxygen on there, where we had one on both sides, then it would have been symmetrical, and so therefore it would have been a chiral. And so that's why we have to be kind of careful with cyclic groups. And we'll give more examples of that later on. All right, and so here they're just talking once again that you have to be really careful with rings and all that kind of stuff. And whereas if we just look at this carbon, this carbon-containing compound down here, we can see that carbon 4 is chiral, because even though it's in a ring, it's got 4 different things hanging off. If we go this direction, it's single carbon, the methyl, and then the double bond. Going this one, it's single carbon, double bond, methyl, and then single carbons. And so going in different orders, going in different directions, you get 2 different orders. Okay. I'm going to try to draw in the inversion center on the on the compound down below. Inversion center, what it is, it's the point through which all atoms are projected. And so I don't like using that term very often, and you don't see it very often, but imagine this point right here. All of the atoms are projected out from that point, so if we notice, if we look at this point, it's similar to a plane of symmetry, but if we look at this point, going this direction one distance, you get the alcohol. Going the opposite direction, you get the alcohol. Same thing here, it's hydrogen, hydrogen, carbon, 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 carbon. So it's called an inversion center. So it's achiral. Okay, I've actually already mentioned this because I wanted to mention it with respect to your hands and the lights, but the only difference is called optical activity, which is just a fancy term here for the way that it rotates light. And so if we look, we have a light source. Oops, let me switch this. We have a light source. If you think back to physics, it's going in all different directions as the transverse wave goes. But if you put it through a filter, you can make it to where it goes through a single wavelength, up and down or left, right, whatever direction. But you're only talking about it's called plane polarized. It's only traveling transversely along one axis. Okay, one plane. I shouldn't say one axis. One plane. Then, if you have your sample that has a chiral carbon in it, it's going to rotate that light. Okay. Then this is what they're showing here. The symbol that they use for rotation for optical activity is alpha. So if it's enantiomerically pure, like if it was just 100% left hands it would rotate it possibly, we'll just say positive alpha degrees. If you had enantiomerically pure right hands in the sample, it would be negative alpha degrees, okay, because they're mirror images that are non-superimposable upon each other. So that's what they're trying to show here, even though I have to say the little eyeball thing is kind of freaky looking. I hadn't noticed that before. Okay, so it's called optical activity. They also call it optical rotation. And the machine that we use to analyze it is called a polarimeter. Oops, I misspelled it. So we would have the analyzer, the polarimeter down here. So in the lab this next week, we're going to be using a polarimeter. It's kind of cool. It kind of reminds me of a turntable. So like if you're just kind of, you know, doing some type of rap or hip hop or whatever, the newfangled music is for you young kids nowadays. But that's what you're doing, is you actually rotating the light with this thing, and so it's a lot of fun to mess around with. But you'll be able to measure the actual optical rotation along the sample. Okay, and sucrose is the one that we actually use in the lab, because sugar itself is chiral. Please don't get scared by this. It is scary though. There's mathematical. Okay, this didn't come out. Okay. So it's called specific rotation. You can't just look at something without putting a polarimeter and saying, oh, that's going to rotate it negative 25.7 degrees, right? But each chiral carbon is going to have a specific optic rotation about it, which is they put in the little brackets, that little alpha. It's supposed to be an alpha, okay? I will not, now I can't say that in the little quizzes as you're reading along and you're mastering, you know, you're doing the mastering part. I will tell you that for the exam, I won't expect you to know this. Okay, this is something that you would just be looking up on your own if you're doing it in the lab or something like that, but you do not need to know it for the exam. However, it is important to know, and I'll explain what RNS means in just a moment, or maybe not today, maybe next class, but RNS is just one way that they are talking about if it's rotating light in the positive direction or negative direction. So one enantiomer is called the R enantiomer, one's called the S enantiomer. And these are ways that the polarimeter uses to measure the exact degree of rotation. And you can also imagine that you can figure up mathematically how much of the right hand, like if we're talking about just like a bucket full of hands, which is really morose, but it's seasonal, right? It's for Halloween. You got a bucket full of hands. And so if we had 100 left hands in there and you've only got like 5 right hands and you shine the optical light through it, it won't be 100% the direction that the left hand normally would be going, okay? So because you have a little bit of that impurity of the right hand, you can actually use the polarimeter and look at this enantiomeric excess that's talking about to figure out what's the percentage of left hands versus right hands in there. So that's why it's really nice. They use this all the time for drug companies in order, like when we talk about levoalbuterol versus albuterol, it's really difficult to get 100% enantiospecific drugs. I mean, it's expensive. That's like saying that you've got, you know, this semi-truck full of hands mixture. You'd have to go through one by one, essentially, to do the resolution. Remember, that's the scientific term for it, when you're separating one thing from another. Do the resolution to separate all the left hands from the right hands. This is getting really morose. Okay, but the same thing happens with the drugs. You know, you can imagine it's kind of difficult to separate when you're synthesizing, you're making this. And the rule of thumb is if you start with achiral compounds, when you end up, whatever you end up will still be achiral. Even if it's got a chiral center, it's going to be a mixture of the R and the S's, or a mixture of the left hands and right hands. Unless you can somehow force it to only select for that way. Our body does that all the time. We make compounds all the time that are different, that are chiral. However, the enzymes force it. It's a chiral environment, so it can only force it to make a left hand or a right hand, because it blocks it from many times making that chiral mixture, both right and left hands. Okay. Oh, I'm not going to go through that part. Oh, except for I wanted to talk about one little term to show. So this is just to show the different amounts and all this kind of stuff. You have the R versus the S, which would be like right hands versus left hands. There's one term. Anytime that you have a mixture for it, so you got that big bucket full of both right and left hands, it's called a racemic mixture. Or sometimes they say, oh, it's racemate. That just means a mixture of the enantiomers. And so that's really important here. Is I just want you to know racemic mixtures whenever you have a mixture of both the left hands and the right hands, or a mixture of both R and S, or plus and minus. Because remember, one of them is going to be rotating light in the positive direction. One's going to be rotating light in the left direction. Okay. Do it on time. Oh, good. Okay. Now we have absolute and relative configuration. 2-butanol we've already talked about. 2-butanol, we have a carbon that's got 4 different things hanging off of it. So it's going to be, we have one carbon, it's got 4 different things hanging off of it. So overall it's going to be chiral. So when something is absolute, what does that mean? Without saying, using the term absolute as definition. Pardon? It's the only way. Faith integration. There are certain things that we hold to be absolute truths, right? Jesus Christ is the Son of God. He died for our sins. That is an absolute truth that we accept in order to become Christians and personally. There are absolute configurations, meaning you can figure up that, the left hand, I'm going to make this up, rotates it positive 25 degrees to the right. So that positive 25 degrees would be an absolute. But then there are things that are relative. This one I can't think of faith integration for. I don't know, maybe personal convictions in that sense. But I can't think of anything extremely faith-based off of it per se. Many times, you would have to have a polarimeter to be able to measure that is positive 25 degrees whenever we go to draw it. Okay? However, they're giving you the answer, giving away the answer right now, right there. However, you can draw 2 different enantiomers and say one of them is going to rotate in a positive direction, one's going to rotate in a negative. I don't know which one's which. I just know that these are going to be the opposite. So we can't say that one is plus and one is minus. Here they've already done it. They figured it up for you. They put in the polarimeter and they're saying the one on the left is a positive one, the one on the right is a negative one. So you can put the absolute configuration down. Okay. So you have to have ways to be able to talk about this, and here they're showing, and I'm not going to. Okay. So once again, we're talking about absolute configuration versus relative configuration. Relative also means that they have the opposite signs of optical rotation. That's where we talk about if one's going one direction, its enantiomer is going to be going the opposite direction. And we have to have ways to be able to differentiate between all of these. Oh, I was really hoping that they would. And I don't know why they decided to end the PowerPoint right there on it, but I wanted to have us end with us going over this idea. So what are the ways, if we go and we just wanted to look at, let's say, these 2 compounds. Okay, we have this compound right here. First of all, is it going to be chiral or achiral? It's chiral, because you can imagine we have a mirror right there. And actually, a lot of times I draw it this way whenever I'm trying to look at things being chiral, achiral. Not one this simple, but there are times whenever I'm trying to draw all when something's got more than one chiral carbon and you're asked to draw out all the possibilities, I literally draw the little dotted lines. It helps my mind think about what happens in the mirror. All right, but we could draw the mirror image. It's non-superimposable. The atom that's closest to the mirror would be fluorine. Bromine's equidistant, and then the one furthest away is going to be the methyl group. However, just by eyeballing this, we do not know which one is going to rotate in the positive direction, which one's going to rotate in the negative direction. We just know that one will be positive and one will be negative. We can, if we anatomically were able to make it pure, to do resolution, we could then stick in a polarimeter and tell. However, we have to be able to differentiate between these two. And so there were a group of scientists that came up with rules to be able to do this. Okay, this is where we get that R and that S. So the R and the S, the group of rules, it's got horrible names. Some of the organic chemistry names for reactions and theories are just stupid. I shouldn't say that. They are just, I don't know. Well, let's just see. One of mine, my favorite ones is when we start talking about like the one that has like name like the word hell and stuff in it, because then it's awesome. But in the sense that it's just stupid. Some of these names that they're named after people. This is called the Gold-Ingold Prelog RS notation. That's why I say, it's a mouthful. I will never ask you to name these, other than to know that this is the RS. I'm sure if I was Ingold, or Prelog, I wouldn't think it's stupid, but it's just a mouthful. And this is the R enantiomer versus the S enantiomer. And so there is a way to actually determine if one is R versus S. Now in biochemistry and biology, they like to use the terms D and L for dextrorotary and levorotary. Like you probably saw that in sugars before. They say, oh, this is D sucrose or L sucrose. It's easy because it's very descriptive. Dextro literally means right. It means it rotates right. The light to the right, levo is left, it rotates it to the left. Okay. So what you're going to do, and the way that to do this is, I'm going to just redraw this a little bit. I'm going to move it over here. First rule, and I actually would sometimes just imagine, remember this is tetrahedral. I would just hold it in my hand, as if I'm holding my hand, and I would rotate it, just like I would if it was a model. You want to put the lowest, always put the lowest priority atom in the back. Okay, if at all possible. It's easy when there's 4 things, and when it gets longer, it's not possible. So if you can't do it, you just have to think, is it going towards you or away from you? Whoops, that's supposed to be you. Because they don't give all atoms equal footing. They're not all created equal in the sense whenever they're assigning the rules. And the rules are priority, okay? And so we're going to leave off right now with just thinking about that, and we're going to pick up discussing the Ingold Prelog RS configuration.